Okay, as we journey through our physics preparation, I'm going to look at photoelectric effect. But just before that, let's get some 10 free marks here that everyone should be able to get under generators. All right, a simple diagram shows a simplified electric motor. Let's quickly do something here. Motor, what type of energy? It's the first one. What type of energy conversion takes place in a motor? Electrical to mechanical. All right. Electrical to mechanical energy. It's already one down. Lovely. What principle are we going to use for electric motors? The motor effect. Don't forget, it starts with the motor. So it's the motor what? Effect. And if I asked you to explain what motor effect is, what would you say? We would then say a wire carrying current, that's the motor effect. A wire carrying current in the midst of a magnetic field experiences a force. And that's the whole idea. Experiences a force. And that is the force that rotates. So if you have a wire that's carrying current and you place it in a magnetic field. Why? In grade 10 when we started, we used to say that a current, if a wire carries current, it generates a magnetic field around it. And that's when we talk about electromagnetism. So if you have a wire, if you have ever seen, let me give you a quick example. If you've ever seen a scrapyard where they lift up cars, they have this heavy stuff that they use to lift up cars. It's an electromagnet. So what happens, they pass current through that metal. Instantly, it becomes a magnet. So it has magnetic field. So if you place that in another magnetic field, there's going to be an interaction. One will be forced to move. So that's how we convert electrical to mechanical. All right, so please take note of what a motor effect will do. All right, is this an AC or a DC? It's a DC. And why is it a DC? It's a DC because it's got what? Split ring what? Commutators. Do we know what B is? What is B? B is known as carbon brushes. And I did explain the purpose of carbon brushes in the other lesson. It passes current from the external, in this case, to the internal, to the coil. So it passes current. Passes what? Current from the external now, because we have the battery, or from the battery to the coil. If it was a generator, it would be from the coil to the external. Okay. All right, Ritumeti, you'll have to follow up and catch up later. Write down the component, the function of component A. What does split ring do? Yeah, it allows current to flow. I see you copied. To flow in one what? Direction. In different halves. So don't forget these functions. These are quick marks that we must get. The resistance R is now decreased. Let's stop there quickly. That's current. What happens when we decrease the resistance? Current would increase because they are inversely what? Proportional. Okay, just wait. But the first thing I see is that resistance decrease. It means current will what? Increase. If you remember the last lesson, I did mention how to, for generator, how to produce more current. And for motor, how to increase the speed of the motor. I did clarify those. I can still show you. It's right here. Let's see, so that you don't say I'm lying. Let me find it. I want to find, yes, you see, how to increase the speed in a motor. 1, increase the number of turns. 2, use a stronger magnet. Number 3, increase what? Current. How do you increase current? By what? Decreasing resistance. Remember, I was saying that your hair dryer, that's what the knob does. When you keep changing the knob, that's what you're doing. That is what you are doing. Okay. No, I've not really read the whole thing. I just stopped there to say, when we reduce resistance, what are we doing? Increasing what? Current. And if you speed of the motor, it increases. That's where the whole thing is going. But these are factors that we need to know. All right, let's quickly answer that question. I need to go to photoelectric effects with speed. Let's see. What effect will the change, choose increase or decrease or remain the same? What's our answer? Increase. Oh, no. It will increase. Okay. Why will it increase? Give a reason for your answer. Less resistance, high what? Current. Done. Less resistance, high what? Current. Which increases the magnetic field around the coil. Are we okay there? Awesome. Some easy 5 marks now. A municipality experienced a temporary power shortage. During this period, the root mean square. We must be able to define this. I don't know why learners forget this definition, though. It is one definition that learners always forget. I'll repeat what I defined the last time. RMS voltage is start from the AC voltage that has the same or that produces the same power, as a DC voltage. And I did show you how to read that from a graph. If I have a graph like that, which one am I talking about? I have that there. Okay, let's make it a bit lighter or thinner. Yep. And that. This is my maximum, and that is my RMS. Root means square. So we've gotten our 2 marks already by defining. And we know where to identify it on the graph right now. It's just below the peak. Calculate the maximum peak voltage during the power what? Okay. It says, during this period, the RMS voltage reduces from what? 220 to 200. They've already given us information. It means we know our VRMS as what? 200 volts. What are we looking for? Vmax. Oh, there's a formula out there. Vmax is what? VRMS over, we're done. 200 over root 2. What's your answer? 1? Are you sure this formula is correct? No. We've changed it. It's VRMS equals to Vmax over root 2. So you guys did not do it. VRMS, so we don't know Vmax. VRMS equals to what? Vmax over root 2. So it means my Vmax is 200 multiplied by root 2. What's your answer? 282. And that's where you should have a mind of presence when you're calculating. The maximum should be higher than the RMS. Check the graph. So when you do your calculations, have an expectation as well. And guys, check your 12 marks in the bag. Boom, boom. Now you have 138 to fight for. Easy. Easy stuff. Okay, I don't want to waste time. We're good. Let's see. Give me 45 minutes on photoelectric effect. I'll try. Photoelectric effect. I'll try. It's not very easy in that time frame, but I have to try. All right. If you look at the word photoelectric effect, there are two things that I see here. I see photo and I see electric. When I say photo, what comes to your mind? Selfies. Yeah? Taking selfies. Pictures. All right. So when we talk about photo, we're talking about light. When we talk about electric, we're talking about what? Electricity. All right. So when we talk about light, what type of energy are we talking about? Light energy. And when we talk about electricity, what are we referring to? Electrical what? Now, this is a hidden question that examiners will ask you. What type of conversion takes place during photoelectric effect? Light energy to electrical energy. So these are simple things that examiners want to get from you. Conversion. So we are converting light. And guys, when we say light, don't think it's ESCOM light. Because somebody's saying, but are we using electricity to produce light and convert? No. We're not talking. For example, a good place to talk about photoelectric effect to be your solar panel. Solar panel, your solar system, works exactly with this. The one you see when people put on the rooftops of the houses works with this. Why? It takes light from the sun and then produce what? Electricity. Some of you have those gray, not the common calculators, this light, I don't know, this other calculators, the bright, the silver one. It has like a panel on the right-hand side. So if you remove the battery of that calculator will still function. Only that it will not function in the dark. I grew up using those kind of calculators without a battery. So to have fun, we used to cover that panel, and you would see the zero go down gradually and diminish and then go off. I didn't know what I was doing, thought I was just having fun. But I was actually doing photoelectric effect. If you know those big cashier calculators, if you go to the store, yeah, this is my friend, they do have it. Okay. So light energy is converted to electrical energy. Now, this is what we're looking at. What is light made up of? Light is made up of photons. And electricity is what? The rate of flow of charges. And when I mean charges, I mean electrons. So basically, we are looking at the relationship between photons and electrons. So if we want to produce electricity, all we are saying is, let's allow electrons to move. Because electricity, we talk about the rate of flow of charges. So anything that causes electrons to move, if you go back to your electrochemistry, anode and cathode, we lose, we gain from the cathode. What's happening? Electrons are already moving. And once you have the flow of electrons, what is it? Electricity. So that's the main aim. The aim is to allow electrons to do what? To move. Now, when I talk about electrons, where are electrons hiding? Electrons are hiding in metals. Grade 10. Metals have what? Free electrons. And that's why they can conduct electricity. There's a whole lot of grade 10 stuff in here. A lot. Okay. Before we go ahead and define photoelectric effect, I'm going to add something to this. Very important, 2 marks again. Light can behave as a particle and a wave. So photoelectric effect explains that light can act as a particle. This reveals the particle nature of light. Photoelectric effect explains that light can act as a particle. So we talk about the nature of light. Light can actually act in 2 ways. So it's a particle nature. Light can act in 2 ways. It can act as a wave, and it can act as a particle. How do I know light can act as a wave? It can be reflected. It can be refracted. That's what we're doing under Doppler. Light can be reflected. Light can be refracted. Grade 10. Okay, and all of those. All right. So these are I've said a lot of important things on this page. One more thing on this page before we move out here is to define what photoelectric effect is. I don't know if you remember. Anybody in the house that remembers the definition? Anyone? Definition. Bibi, you're covering your face. It is the ejection of an electron from the surface of a metal when light of suitable frequency, and that word is important, when light of suitable, I'll show you something just now, frequency shines on it. Not everyone that goes to the mall buys. You know that, women, you know. This is not gender, just saying. Women, you know that. Just drive out for window shopping. Not everyone that goes shops. Window shopping. You must have, for you to shop, you must have suitable money. Ooh, that shoe is nice. All you can do is check it with your eyes. You come back. Okay, it will be gone. Yeah. Or you go, I know people who go to a perfume store. Oh, this perfume is nice. Tester. Every day on their way to work. Different stores. All right, just testing. This is nice. Everybody, when they get to work, they, oh, you smell nice today. It's one of the many perfumes I have. Meanwhile, it's just a stop in the mall. So for you to be able to eject electron from the surface of a metal, we need to shine what? Light of suitable frequency. Let me show you a demonstration quickly of photoelectric effect. I've got my little demonstration here that I use. All right, this is my demonstration that I'm going to use for you. So what I have here is, I've got a metal. Now all I'm going to do is to shine light. I'm using, if you look at the top here, it says sodium. So I am using sodium metal. I can change it, and I'll tell you why we can change. Zinc. All right? I can use copper. I can use platinum. I can use whichever one. All right? And my light, check. I have infrared, grade 10. Then we move to visible light. Red, orange, yellow, green, blue, indigo, violet. And then I come to ultraviolet. Ultraviolet is where you have your X-rays, your gamma rays. Your infrared is where you have your microwave, telecommunication waves, and all of those. If you remember that in grade 10, where we had this colorful picture with a rat somewhere there. Yeah, some textbook would have a rat, a snake. A snake has infrared in the eyes. Okay, you guys, I don't know where you were in grade 10, but like that. Okay, just on. You're the COVID ones. Okay, COVID 10s. All right, I'm just rubbing it in. Anyway, check this. I wanted to see something. Do you see just below here? It says current is what? 0.00. We are not producing any current. Why? We're not even shining any light. Let me just quickly demonstrate to you. I'll come back to this. I'm going to shine. I want a high energy light. Do you see? Immediately electrons came. Do you see that current was 0 before? It's now what? 0, so I have produced what? Electricity. How? By shining light on a metal. Let me show you photons in itself. What photons is. I'm going to define that now. Show photons. So when we show photons, that's what it looks like. So when we shine light, we're shining little particles of energy. Those energies are now transmitted on a metal, and the electrons on the surface of those metals are released. Once they are released, remember, the release is called electricity, the flow of current. Unfortunately, Lungile, you are the COVID ones. Okay, guys, we're going to look at the impact of what I'm doing later on here. Okay, if I change to red, what happens? I don't know if you notice an effect here. Okay, there's an effect. Oh, kind of as if there are no more electrons. I'm going to tell you why. What if I go to that? Now we have electrons. We are going to see what's going on as we continue this. And we can draw our graph. I'm sure those of you that have done this topic, you've seen that graph. You must have seen that graph. Current versus intensity. Okay, there's a graph there. All right, let me explain. So this is the whole of photoelectric effect. I normally divide photoelectric effect into 3 parts. Number 1 is to talk about the light. Number 2 is to talk about the metal. Number 3 is to talk about the electrons. And we're going to do that very, very fast. So that's the whole thing we are studying. 3 parts. Part 1. Part 1. Part 1 is to talk about the light. I'm going to run now. Let me see, 7 minutes on each, if I can. Part 1 is to talk about the light. We said light is made up of what? Photons. Light is made of photons. The question is, what are photons? Photon is defined as a packet of energy. Is a packet. The word packet simply is called a quantum of energy. That's why this is called quantum physics. Please, when I say quantum, don't think of a taxi. Different worlds for quantum. All right, talk about the galaxies and all of those. It's part of it. It's very wide. It's a very wide concept. Okay, but as long as you're not thinking of taxis, I'm fine. Thinking of those white things, white combis. No, it's a quantum physics. It talks about energy of an electron. Packet. It's just a packet of energy. Yeah, quantum can be called a packet of energy. All right, and now quickly, how do we define this energy? This energy, E, can be defined as HF, where H is known as your Planck's constant. There's a C there somewhere. And what is F? It's the frequency. Oh, frequency of light. Ah, interesting. We're going to quickly go into that. And guys, there's no need to cram this formula. What would you notice? Since H is a constant, can I then say E and F are directly proportional? The higher the frequency, the bigger the energy. Let me shock you with something that you don't know. It's a phenomenon that you've not thought about. Okay? I'm sure you know this. Which one has this frequency here? It's violet. All right? If I take you back to Doppler effect, redshift means we have a long wavelength. And wavelength and frequency are inversely proportional. All right? So this one has a high what? Frequency. And this one has a low frequency. Let me just show you something very, very nice. I want you to get something here. And in case you forget, use this explanation that I'm going to talk about now. There are 3 types of sun images, the sun, that we get. There's the yellow sun during the day. Right? There's the orange one when it's setting. When it's fully set, it looks a bit reddish. I don't know if you've observed the moonlight kind of sun. Which one is the hottest? The yellow one. It goes back to this. The frequency of yellow is greater than the frequency of orange. Yeah, than the frequency of. Since frequency and energy are directly proportional, it means a yellow frequency, a yellow light has more energy than the orange, than the red. It's amazing how science just explains all of this. I don't know if it makes sense. That the yellow one, it's very hot day. But as the sun sets, what happens? Orange, and then, like right now, I'm sure it's a bit red, you know. They say the sun is crying now. You know, those kind of English metaphors, and I don't know, is it metaphor they call it? Whatever they call it. All right. But I hope it makes sense. Your electric stove at home, when you get back home, try it. It's not red. Because red is not as hot as orange. They are orange. I know you always say it's red hot. No, that's a wrong science. Say red is the hottest. No. If you go to places where they are dealing with metals, they don't use red flame. They don't use orange flame. They use a blue flame. Why? Blue has a higher frequency. Therefore, the energy that blue radiates is hotter than your red. Same thing with the infrared. So if I tell you now, guys, that which one has the highest energy, is it infrared or ultraviolet? It's ultra. Your ultraviolet is where you have your X-rays. I used to do this a lot when I was young, you know. I'm still very young, but when I was younger than this, I'm watching cartoons and my dad walks in and I put a little paper by the remote sensor so that he cannot change the channel. Like put a book there, you know, but something, as if you forgot something. But he's busy pressing, he wants to watch the news. But he cannot change. Why? We're watching cartoons. And he's thinking, what's wrong with this thing? And we are dead laughing. Myself and my sister. But wait, what I didn't realize then was, in your remote, it's infrared. Doesn't have enough energy to pierce through the paper. As compared to X-rays. X-rays would pierce through the skin and take the picture of the bones. So X-rays have a higher what? Energy. Why? They have a higher frequency and they have a very short wavelength. I want you to see, if you can see, those of you at home, if you can see the screen, my ultraviolet, check, you see that's the wavelength, 100 nanometers. Check red, 700 nanometers. It means it is longer in wavelength. And the fact that it's longer in wavelength means it has what? A low frequency. I don't know if you're bringing everything together. All right. Lovely. Okay. So E and F are directly proportional. They're going to ask you this, and we're going to come back to this. The higher the frequency, the higher the energy. However, there is something important that I want us to see. We know that C equals to F lambda. I don't know if you remember that formula. For speed, for sound, when we're doing Doppler effect. Yes, Idris, that flame thinging that welders use. Good. That flame thing. It's called an oxyacetylene flame. It's very hot. Oxygen. Acetylene. Acetylene is your organic chemistry now. Acetylene. Acetylene, Lyne. It is your ethine. So it's oxyethine flame. Yeah, so it's called oxyacetylene flame. Okay, let's leave all of that. Now, please quickly check. C equals to F lambda. Okay. So, for speed, for Doppler, we use V. Right? And for light, we use what? C. They are both what? Speed of, one is speed of sound, one is speed of light, but they are both speed of what? Waves. So this one is talking about what? Light speed. I hope you remember that that's a constant. What's the value? 3 times 10 to the power what? 8 meters per second. For sound, it is 340. Light travels and sound. I'm sure you know that. You can check from your phones. You see the lights before you hear the when you take a picture. You've never noticed. Should you take a picture and you hear the sound before the light, please run away. It's a movie set. Oh, sorry. No. Okay. All right. Okay. So light speed, 3 times 10 to the power 8. And you know what? How I always remember it, I use C. And for speed, I use V. It's very important that you know. Because if you go and bring in 340 here, already you are lost. What do you do with light? You see. What do you do with light? You're talking about letter what? C. All right? Good. If I take my Golf now and put some things in the exhaust and tap the engine a little bit, what do they call it? They call it the vrpa. You know, when you drive the ta-ta. The V is sound. I don't know if it makes sense. The vrpa, sound. But with light, what do? I see. So know when to use C. C is light. V is sound. Okay. All right. Now, yes, V is the speed of sound waves. C is the speed of light waves. All right. So, what we have here, you would now notice that if I divide both sides by wavelength, what would I get? C over lambda equals to what? F. Oh, and because this one is a constant, what do we know? Frequency is inversely proportional to wavelength. Please, this is very important now. Frequency is inversely proportional to wavelength. So that means if I have E equals to HF, I could simply replace this. What is my F? C over wavelength. I'm sure you've seen that formula. So in that same way, E is inversely proportional to that. Why are we saying that? Because this is a constant. H is a constant. C is also a constant. Guys, we cannot talk about proportionality if there's no constants. Okay, so we've created two things just now. E and F are directly proportional, and wavelengths are inversely. Guys, that's very important. You'll see where examiners will throw these questions at you. Multiple choice. It's coming. When you have absorption and emission spectrum. All right, so we said I'm still dealing with light, by the way. Let's revise quickly. Light is made up of photons. What are photons? Photons is defined as the packet or the quantum of what? Energy. How do we measure the energy? Oh, what's the unit? Joules. Remember, right? Joules. Capital J. All right, E equals to HF. H is Planck's constant. F is frequency. We just described the higher the frequency, the higher the energy. Then we also know that E equals to HC over, guys, don't panic. Your formula page. I think I got one here. The formula is there. So don't panic. Do you see H E equals to HF there? There we go. So do you see this one here now? V equals to F lambda, but I wrote C. Why? V is for what? Sound. Make sense now? But C is for light. So V is the speed of sound. C is the speed of what? Yeah, this one is now for Doppler effect. Where this one is 340 meters per second. But then we also know that C equals to F lambda. This one is also what? Speed. But it is speed of what? Light. So this is the formula we've played around with. E equals to HF and E equals to what? HC over wavelength. So there's no need to cram the formula. They just understand what it means. And should you forget the relationship, use that to define the relationship. E is directly proportional to F, and E is inversely proportional to what? Wavelength. And with that, can we move on? All right. A few more things on light. I need to increase my pace. Okay. So we're still on light. Is that okay? So we talk about light and all of those. Let's talk about something here just before. Intensity and energy of light. Intensity and energy of light. All right, I'll look at intensity first. Intensity refers to the number of photons. So when you talk about high intensity refers to a bright light. And when we say a bright light, we are saying what? It contains a high number of photons. So when you see a bright light, the number of photons present are actually very high. It means my low intensity would mean what? A dim light. So take note of those words that examiners would use. So when I say low intensity, it means we are referring to what? A dim light. And it talks about what? A low number of photons. I'll show you again. When you get home, you can download this on your laptop and just check it out. Just go to PhET. I can send you a link if you want me to send you the link. And play with it, Just enjoy physics. I know you are writing. Okay, but just take a look at this. Do you see on top there, what do you have? Intensity. I am going to keep it as red so that we can use a light that is very visible. Check this. I know what have I done? Increase the intensity. Do you see it at 100? Do you see the number of photons? They are more. If I reduce intensity to 15, do you see the impact? Let me show you with light. Check that light. Let me increase the intensity. See, it's brighter now. Let's go to blue. Maybe a blue light will be better. Somewhere there. All right. Check the intensity. Intensity. It's kind of light. But if I increase the intensity, what have I done? I have opened more photons to it, right? So we say it's high intensity there. Okay? And it means we're talking about what? Bright light. So these are keywords. Examiners will talk about intensity or talk about what? Bright or dim light. All right. What will this impact on? High intensity of light means more photons are released or shown, let's say, or released to the surface of the metal. I think, let's say, shown to the surface of the metal. And what is the impact of this? This will increase the number. This will increase the number of photons. The number of photons with the same kinetic energy. I'm going to show you that as we continue and bring you back here with the same kinetic what? Energy. The number of photons will increase the number of electrons, but the kinetic energy of the electrons will remain what? The same. So high intensity of light means more photons are shown to the surface. Shine on. Because I changed it. I said released before. Shown on the surface of the metal. This will increase what? The number of photons with the same kinetic energy. Check how an examiner wants to trick you. Let's catch them. Let's catch them quickly. This is intensity. And this is kinetic energy of photons. The kinetic energy is going to remain the same. So what will my graph look like? There we go. However, if I have this intensity and I have number of electrons, I'm going to do something here for you. Or current reading, ammeter reading. Since we are producing current, if we increase, this I need to go to the next page to explain. I'm going to go to the next page to explain that. But just know that the number of photons only affects the number of electrons. Number will only affect what? Number. It's in most cases the last or second to the last question. Check any question, you'll see it. Intensity is increased, intensity is decreased. What happens? Okay, let's see something here. Let me go to my demos. Let me go to my simulation. All right. I want you to watch. Please try to keep an eye on the number of electrons. Is that okay? I am going to, let me say, show only highest electrons. Okay. Look at the intensity here. It's at 12%. All right. If I increase intensity, see, I'm using the same light, right? But what am I doing? Increasing what? Intensity. I want you to check the value of the current. What's the current now? 0,019. I want you to check the number of electrons that is being ejected. Start at that. But let me increase intensity of the same light. What happens to the current? It has increased. What happens to the number of electrons? It has increased as well. But do you notice they are still moving at the same speed? Try to check. They're still moving at the same what? Speed. But the number of electrons, if you want to see that very well, check that. Can you see the speed? The speed did not change, even if I change intensity. For you to show that, for me to show you that the speed did not, watch this speed. Do you see the speed now? Do you think this one is faster? Yes. What did I do? I changed the light. I keep the light as blue. Check. So the speed, we're looking at this now. Speed. See that the speed has reduced, right? But let me change intensity. The speed is still flowing like that. So intensity affects what? The number of photons, which affects number of electrons. But energy remains what? The same. All right. That's why I said high intensity of light means more photons are shown on the surface of the metal. This will increase the number of photons. Let me also say, increase the number of photons. I've made a mistake here. This should increase number of electrons. Sorry. I know you don't want the T-pex. Just T-pex the thing. Number of electrons with the same kinetic what? Energy. Therefore, current, which is known as, an examiner will tell you, ammeter reading, will also what? Increase. Current will increase. And the current is ammeter reading. Okay. I hope I'm going so slow so that you don't even need to read this again. Just follow through. Just answer questions now. Okay. Let me do a calculation here. We're still talking about light. Is that okay? We're still talking about light. Now, how do we measure current in physics? I equals to Q over what? Delta T. Do you remember that? Grade 10. What is Q? Q is what? The quantity of what? Charge. Combine this with electrostatics. In electrostatics, N equals to Q over QE, where the QE is the charge on an electron. So if I cross multiply, what happens? Check. Q equals to what? NQE. Oh, it means now my current. What is my Q? NQE over what? Delta T. What does it mean? It means, and I wanted to take note of what I'm going to do here. The higher the number of electrons, the bigger the current. And do you know what causes the number of electrons to increase? More photons. I don't know if you are connecting the whole thing. When you have more photons, you are going to have what? More electrons. There is a summary. If I increase intensity, what will intensity affect? Number of photons. If the number of photons increase, what's going to increase? The number of electrons. What will increase? Current, which is your ammeter reading. So it's just a flow. It's a flow there. But we say the kinetic energy remains what? the same. So please take note of that. EK of electrons remains what? The same. All right, I'm done with that. One more thing on light, and then we can move on. Guys at home, are we good? I know some of you now, it's a revision for you. Are we okay? And those of you that even say it's a revision, I'm sure you're getting some new things. Guys at home, all good? I know it's not revision for you, Taban. That's why I'm taking it a bit slowly, because I know some of us, I haven't done this, so I'm taking it a bit slowly. All right. What did I talk about now? Intensity. Let's talk about the energy of light. This is intensity. Let's talk about the energy of light, and then we are done with that. Energy of light. Wait, what affects energy? Let's go to our formula. E equals to what? HF. What affects energy? The frequency. Is that okay? So it means a change of light to a higher light of higher frequency, a change of light to a light of higher frequency does what? Changes the energy of light. So if I want light with a higher energy, what should I do? Use a light of higher what? Frequency. A change of light to a light of higher frequency changes the energy of light. And what happens here? A change in energy, or a higher photon, I'm going to say, a photon rather, with high energy will eject an electron of higher what? Kinetic energy. By the time we finish, you'll be able to connect all the dots. But the number of what? Electrons remains the same. However, current increases because of a shorter time. A shorter time. I don't know if that makes sense. That current will still increase. Okay, good question. I know that's where you want to catch me. But I will catch you first. I equals to what? NQE over, that's where I'm catching you, over delta T. I and delta T are what? Inversely proportional. So the shorter the time, the higher the current. Because we're talking about the rate of flow. So if it flows faster, make sense now? Good. But what I needed to see is that the energy of the photon will only affect the energy of the electron. The number of photons will remain what? The same. However, current is still it's traveling at there's a shorter time of travel right now. So more electrons would flow. What? Let me write that. More, okay, let me say high moving electrons will flow at a small time frame, or in a small time frame. In a small time frame. We're saying I is inversely proportional to time. So examiners are going to want to trick you, and the whole idea is, do you understand the topic? That's what the whole question would be. Do you really understand the topic? If you understand, then we can play around so many things. Okay. So whichever way, summary of this, number of photons will affect number of electrons. Energy of photons will affect what? Energy of electrons. That's the summary. Number of photons will affect what? Number of, it's number to number. Energy to energy. But current will increase in both. Why will current increase in the first one? Number of electrons are increasing. Why will current increase in the second one? Because of the shorter time. There is a higher rate of what? Flow per second. Make sense, everybody? Okay. Let's move. We're done with light. So how will examiners tell you this? They tell you that we started from blue light. Now we are in green. They're going to change it. Started from red. Now it's changed to infrared. Just remember the arrangement. I hope you remember the arrangement. What's the arrangement? Red, orange, yellow, green, blue, indigo, and violet. This is how I remember. You know what is next to red? Infrared. What is next to violet? Ultraviolet. And what's happening to frequency? As you go down, what's happening? Frequency what? Increases. And as frequency increases, what happens? Wavelength does what? Decreases. And as that happens, what happens? Energy increases. So at least you will remember the sun, that the yellow sun is higher than the energy of the orange sun, higher than the energy of the... Let me ask you something. If for those of you that drive at night, let me quickly paint a picture to you. You see guys that wear overalls, and they wear luminous things so that people don't hit them on the road, right? You've seen those, you know, those working overalls, and they have those bands that are luminous. What color is it? Yeah, those reflectors. The reflectors. But do you know that you hardly get red reflectors? It's good. The whole idea is it's yellow, orange, not red. Why? You want people to see, so you need a light of high energy. So it can be red. If you are working in a place, they give you the one with red. Tell them they want to kill you. Please just tell them, I see you guys. Do you have the one with blue, please? Because I want people to see when they are coming. Why? It radiates a higher energy. So if they give you red, know that they've given you obituary or whatever it is that they are giving you. All right. I hope it makes sense. Everything is connected. Okay, guys. So do you see, some people say, all of these things we are learning, where are we going to use them? We are using them now. ESCOM hires me, gives me an overall, and I see it's a red. Please, I change it. Maybe the managers have blue. Managers, you have blue. I'm also a manager here. So all of this talks about what? Light. Higher energy being what? Radiated. All right. We're done with light. Let's go to the second phase, part 2, the metal. Part 2 is to talk about metal. Why are we talking about metal? Metals are a house of electrons. This one is very short. Metals are the house of what? Electrons. That's how I call them. House of electrons. Okay. Metals have free electrons. Metals have free, delocalized. Let's go back to chemistry. Grade 10. Electrons. All right. Free delocalized electron. They have one electron which they all give out one in the outermost shell. You remember that? Group 1. Okay. Okay. Now, in a metal, we have what we call work function. We have work function of a metal. Work function of a metal. What's the symbol? W naught. And this is defined as what? The minimum amount of energy required to eject an electron from the surface of a metal. And work function is measured as H multiplied by F naught, where this one is called the threshold frequency. Or, let me give you the other word, cut-off frequency. In case you don't see threshold, you must know that it can also be called a cut-off frequency. No, it's not work, power, and energy yet. But it's still energy. We're talking about work. So you would see that W. Remember, work is energy. Okay. Now, what is threshold frequency? I want to define something here. I don't know how you're going to write the notes, but okay, let me just define it. I want to say something. Before I define, let me write it in yellow. Different metals have different work functions because of different ionization energy. Grade 10. What is ionization energy? I won't go deep into it. Ionization energy is the energy required to remove an electron from the outer shell of a metal. That's grade 10. So in grade 10, we spoke about the first ionization energy, the second ionization energy. You don't remember stuff. All right. So the first ionization talks about the energy required to remove the first electron. And the second. I want you to see how it's connected. Here, what are we also doing? Removing electrons. Okay. Now, let's define threshold frequency. Threshold frequency is very similar to work function. The only difference is what? The word energy. So this is the minimum frequency of light. All right? Required to eject or remove, whichever word you like, an electron from the surface of a metal. From the surface of a metal. And we can also calculate this by saying HF naught, which is equal to HC over lambda naught. Everything has a naught here. And what is this? This is called threshold wavelength. By the way, I'm sure we know that wavelength is measured in meters. I'm done with the second part. Very short. Work function. Minimum amount of energy required to eject an electron from the surface of metal. Different metals have different work function because of different ionization what? Energy. Threshold frequency. We're still going to come back to all of this. Let's look at the third one. Third one also is going to be very fast. Then we combine. I'm done with number 2, Kwanele. I'm done with number 2. Finished. I'm done. Nothing missing here. I've mentioned threshold frequency. I've mentioned threshold wavelength. Nothing missing. Nothing. What did I forget? Okay, maybe just one. It's not that I forgot, but just to remind you for your own sake that work is measured in joules. I mean, like Okay, I didn't forget. That we did with under intensity. The number of photons is directly proportional to the number of electrons. That's why I drew a graph there. Part 3. Oh, this movie is long. Part 3. Part 3 is talk about the electrons. Part 3 is talk about what? Electrons. Electrons move. And this is known as current. Remember we said, current is the rate of flow of charges. So when we have current electrons moving, we're simply saying current is being produced. And if we say something move, they move. What type of energy are we talking about? Kinetic what? Energy. Kinetic energy. And how do we calculate the kinetic energy? It is half mv squared, where m is the mass of an electron, which is also a constant. 9.11 times 10 to the power negative 31 kilogram. There's no need to cram it. It's there on your formula page. 9.11. It's so tiny thing, It's negative 31. If they tell you weigh this, you should be worried. In fact, you cannot weigh this. If your weight is 9.1 times 10 to the power negative 31. 0.00. There are 30 zeros before a significant number. It's so light. So if you are weighing this, there's a problem. All right. So kinetic energy. Now, please don't forget what determines the kinetic energy here. 2 things will determine the kinetic energy. What determines factors that determine the kinetic energy? Factors that determine kinetic energy. Number 1, energy of photon. And number 2, the work function of the metal. So a high energy photon, and we've talked about how to increase the energy of a photon, right? What do you do? How do you increase the energy of a photon? Change the light. Use a light of higher frequency. High energy photon will release a high energy electron. A low work function metal will release a high energy electron. Why? EK is equal to E minus work function. And that you can get from the formula on the formula page. So everything I just explained now with factors, I just picked from that formula. If my energy is high, my kinetic energy will also be high. If my work function is high, my energy would be low. Use formulas. I don't know if that makes sense. Just use numbers. All right. Check here. If I say 10 minus 4, what's your answer? 6. If I increase the energy to 12, keep the work function. 12 minus 4. You see 8. What if I keep this and increase the work function. I don't know if you see the method I'm using. So, affected by these two. High kinetic energy. High work function, low kinetic energy. Just use formulas and enjoy yourself. All right. By the way, for now, I am done with electrons. For now. And there is that famous diagram that we all know. I'm sure we know that famous diagram. That combines the three. We looked at three things, right? So we have light shining on a metal. Okay. Okay. This is what I'm talking about, though. This is what I'm talking about. If I want to summarize everything I've done here, I have a metal. And what do I have in this metal? I have my work what? Function. What do we have shining on this? Photons, right? I'm sure you know this diagram now. So we have lights shining. And what do we have living? We have what? Electrons. Okay, so what is this? Photons. Remember how we defined it? Quantum of energy, which is HF, or E equals to HC over lambda. Here we said work function is equal to HF naught. Then what do we have here? Kinetic energy, which is what? Half mv squared. These are your electrons. And this is where we produce what? Current. I equals to N QE over what? Delta T. Here also we said work function is equal to HC over threshold frequency. So this is what is happening. That's why I divided it into three parts. Part 1, Part 2, and Part 3. We good? And our formula is what? E equals to work function plus kinetic energy. There's no need to cram that formula. All I'm going to show you is interpreting now. We calculate. Oh, done. I need to quickly teach you now interpretation. And this has to do with graphs. Okay? This will affect you in 8 topics. Whatever skill, you're shocked. Whatever skill I am going to teach you right now on graphs. 8. Let me list them for you. Newton's laws, that's number 1. Vertical projectile, that's number 2. Momentum, that's number 3. Doppler, that's number 4. Electrostatics, that's number 5. I've actually measured the whole topic. Electricity, that's number 6. Electrostatics, that's number 7. Photoelectric effect, same paper. Yes. All right. So it's just a skill that we spread across the paper. So let's look at graph skill. Interpreting graphs. Graph of photoelectric effect. Graph of photoelectric what? Effect. And you remember that graph that we saw earlier on when we were playing with the simulation? Okay, so we're going to start with the frequency here and kinetic energy there, and that's 0. What happens is this is what your graph would look like. And then we call this extrapolation. We create extra points. I'm sure you've seen that graph. You've seen that graph. Everyone must have seen that graph, whether you understand it or you don't. You must have seen that graph. Okay. I'm sure we're drawing. Now we're going to use laws of mathematics to deal with it. Laws of maths. Okay, all right. Guys, check this. This is the graph we have. The first thing I'd like you to see, guys, when you see a physics graph, remember, 8 topics now. When you see a physics graph and it's a straight line, bring your maths in quickly. What is your straight line graph? Y equals to mx plus c. Please bring it in without even making any fussy face. Say, but this is physics. Why are they bringing it? Oh, please. Y equals to what? Mx plus c. Let's interpret. What is m? Gradient. What is c? Y what? Intercept. Quickly. That's what we do. No matter the topic, whether it's Newton's laws, whether what. Vertical projector. We're done. The same concept. That's the first thing. Now the next thing is think of the formula of that topic. The formula in this topic is what? E equals to what? Work function plus kinetic what? Energy. That's the formula. Are we okay? Bonga, your eyes say, I'm waiting to see what this guy is going to say. Check this. It's very interesting. It's the same thing, sweetie. It's just maths. Okay. And it's on the formula page. All right, everybody, look at this quickly. One skill, 8 topics. Or let me say one skill, the whole of physics. All right. What is on my y-axis, guys? Kinetic energy. What's on the x? Frequency. You've got to arrange this formula to suit y equals to mx plus c. You see where the y is? Put ek there. You see where x is? Put frequency there. We're going to play around with it. Let me show you. So I see that this is my y. Right? And that is my x, whoever the x is. Okay, whatever the x is. So that's x and that's y. Now, let's see. Can I make ek the subject formula so that it stays where there's y? What will I do? Can I bring this here? What do I have? E minus work function equals to, make sense? Do you see my first step? My y is sorted. I hope you understand what I mean by my y is sorted. My y is ek. They are in the same position right now. I have a problem. My x is f. I'm checking this formula. Is there f? Huh? There is, though. Yes, under energy. Do you see that? Do you know I'm done with this already? Because what is my formula? Y equals to mx plus. And that's the simple skill that affects you 8 times. Simple skill like this, 8. Check. What's on my ek? Y. What's on the x? Frequency. Do you see they are in the same perfect position? It means I can then compare. What is m? M is age. What is c? Work function. Hold on. Guys, look up quickly. I need to get something here. I want this thing to sink in. Do you notice that the gradient of a straight line, what is it in math? Analytical geometry. Is constant. That's when we talk about collinear points. The gradient, look at the word I'm using. The gradient of a straight line is constant. Wait, what is my gradient here? What is h? Planck's. Makes sense. The gradient of a straight line is constant. In this case, my m equals to h. And what is my h? Planck's what? Constant. You see that word constant coming in again? That's why it's a constant. So m is equal to what? H. What did we say our c is? I want you to watch something. C is what? Do you notice the y-intercept is below 0? So it's a negative value. That's what negative stands for here. It means this point is my work function. So an examiner is going to give you a graph. You've got to interpret. All right, guys. So examiners are going to give you multiple choice questions or structured questions, and then you see something like that. Are we okay with what I've done so far? So you would see it's a negative value. It doesn't mean that the work function is negative. No, it's only telling you look below 0. What is this point? That is your x what? Intercept. And what do we know about x-intercept? Y is equal to 0. I'm going somewhere with that. Let's quickly interpret that. At x-intercept, but what's on my y? Kinetic what? Energy. Okay. Please somebody remind me, just immediately after looking at graphs, what are the conditions for photoelectric effect? Don't want to forget. 0 equals to what? HF. Let's play. Can I bring the W naught to the side? What am I going to have? W naught equals to what? HF. Oh, what is W naught? It is HF naught equals to what? HF. Can we divide both sides by H? Yes. What are we going to get? F naught. It means my x-intercept is known as the threshold what? Frequency. Check physics and maths. This is where they get married. Graphs. We are in the welcome to the holy matrimony of maths and physics. Is there anyone who would wish that these two should not be married? Rather say now or forever hold your peace. Unfortunately, they got married before you started school. So you cannot hold your peace. But this is just where they got married. Physics and maths. Okay, it's a very tight relationship. Guys, are we okay with what I've just explained? So examiners are going to give you graphs. Guys, please, no matter the topic, look at your Y, look at your X, rearrange it. Is that okay? Rearrange it. Make sure Y is where it is, X is where it's supposed to be. Compare your other variables, and you're done. You'll be surprised. Mpumalanga last year, they came up with a graph on Doppler effect. Yes. The formulas. Yeah. No, it's not millions of formulas. It's the main formula. If I go to electricity, I'm just going to use what? EMF equals to what? I into bracket R plus R. That's the main formula there. It's the formula in electricity. If I go to vertical projectile motion, VF equals to what? VI plus A delta T. If I go to Newton's law, F net equals to MA. Yeah. Check the Y and check the X. Yeah. Good. Check what's on the Y and check what's on the X. Does that answer your problems? Good. Yes. Check what's on your Y. Check what's on your X. It must be in the formula you are going to use because you've got to rearrange them as y and x. Even this one, I'm going to do something else now. Are you okay with this one, though? Check this. Check this. I like it when I say check this. It means something is coming. Check here. Check this. Check this. Check, 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 check. I'm going to change that frequency to 1 over wavelength. The graph remains the same. But I want you to see, check what I'm using. I'm using EK and 1 over wavelength. Find the formula of the topic that has those two. The question is there a wavelength here? Yes, there is. EK equals to what? HC over, do you see that? Can I extract that? EK will be equal to what? HC 1 over wavelength. Do you notice I am done? Y equals to what? MX plus C again. You see my C is not changing. My Y is not changing. What has changed? My M. What is my M now? What is my M? HC. Oh, by the way, check. What is H? Planck's constant. What is C? Speed of light, which is also a constant. If it's not a straight line graph, then I cannot use y equals to mx plus c. But go and check all your physics. It's all can be represented with a straight line graph. Even if it's inverse, if something is inversely proportional. Okay, wait, guys, I wanted to say something. I thought I would be able to get to it. Look, I'm just passing through questions right now. Okay, I'm just passing through questions. We are going to get to this one. Oh, check the first thing we see here. Look at 10.1. Write down the name of the physical quantity represented by F1, threshold frequency. I am done. Make sense? Elena is thinking, oh my God, they didn't teach us this one. Check 10.5. The what? Intensity. Actually, it's the last one. The intensity of the light is increased while the frequency of the light is kept constant. We have answered this. How will this affect the reading on the ammeter? It's in your notes. What's the answer? It will increase. Done. 1 mark out of 150. Already. Check. Did we define work function? Oh, 2 marks. Done. The 2 here, they are calculations, which you use your formulas to get. There's nothing in this. Do you see this 11 marks? Psh, I'm done. Just 10.3 and 10.4. You're just going to substitute the things you have. And the best way to do physics, write out the things that you have, look for the formula, throw them in, bring in maths. They are married, by the way. Check. I wanted to check the next question. Okay. Oh, photoelectric effect confirms the particle nature of light. We spoke about that, right? I was just cutting and pasting these questions. I didn't even read. I just wanted to see the whole thing. The work function by means of a calculation. You see number 10.1.4 is what I told you to remind me of. Conditions for photoelectric what? Effect. I'll give them to you just sharp. Okay? Increasing energy. We're going to talk about that. We have our formula. Okay, all the constants are here. Formulas are here. Check this. Do you know that these lines are parallel? Analytical geometry. Parallel lines have equal gradient. Do you know the gradient there? Let me tell you an easy way to remember your constant. Check your x-axis. What's on the x? F. Write the formula for E. E equals to what? HF. That's my gradient. If this is 1 over lambda, write down the formula for E again. E equals to what? HC, which is HC 1 over, that's my gradient. F and lambda. Now, your kinetic energy is a dependent variable. What happens? As we change the frequency, the kinetic energy of the electron changes. So kinetic energy would be your dependent variable. You cannot change the kinetic energy without changing the frequency. It's not like you're going to grab electrons and slap them. Move fast, you, move. Then you, follow. No. What do? If you want the electrons to move fast, what do? You change the frequency of... It's like, the way I normally explain this is, guys, if I'm going to the shops, I will, Lungelo. If I'm going to the shops, I want you to think about this practically. I'm going to buy chocolate in the shops. Are you aware that the same chocolate costs different in every shop? Chocolate in ShopRite is different. That's why women, I don't do shopping with women. They know the price of milk. Checkers. They compare. I tell my mother, I'll wait in the car. When you are done, call me. I'll fetch the grocery. Because my mother will check for it. No, in game, it is 15 cents less. Do you even know women will make you move from one mall to the other without considering the petrol? Because they are thinking it's cheaper. But you are going to drive first. You have no idea. Guys, it's the other gender. This gender is powerful. But check, I want to buy chocolate. So, where do I get chocolate from? The stores. I want to explain photoelectric effect with something we do every single day. Chocolate at ShopRite, let's say 15 rand. Okay, a big slab. The minimum amount I must go in with is the amount they are selling for. I am the photon. I am going to remove Electron, which is chocolate, from ShopRite. Hold on. The change that I am going to have, let's say my uncle is sending me, and every time he sends me, the change is mine. So here's my uncle who sends me with 15 rand, and the chocolate is 15 rand. Change is 0. I am going to walk so slowly, no life when I'm going back home. Somebody test, you stop me. Hi, sir, how is the maths test? We will talk and talk and talk because the change is not interesting. It's 0. He comes the next day, gives me 50 rand to go and buy the same chocolate. How much is my change? 35 rand. When you stop me, I'll say, Tess, can you walk with me? Because the faster I give him the chocolate, the quicker I get my change. Do you notice I'm motivated by change? Now, the change means I am moving what? Faster. Why? I went in with higher money. He now gives me 200. I'm sure you should know this better. He gives me 200. I even forget what I'm going to buy. Because I have to rush to the... You know those cartoons? Yeah, where your leg runs on the spot first. Then you... Good. Because I know the change is what? Mine. I want you to imagine. So I am the photon. I am going into the shops. The minimum amount I need is 15 rand. Do I have more than excess? Yes. What is the change? 185. That's the energy that drives me to run back. That's my kinetic energy. Make sense? Then he gives me a check. Or he gives me, Bill Gates then sends me chocolate. Says, buy anything you want. You know, I'm just going to I'm not even going to go to ShopRite. It's too expensive. I'm going to go to the cooler shops and give them money. I go and buy a car. I drive faster home. The change is very big right now. Do you notice the more money I go in with, the more change I have? Which means my energy affects the energy of the electrons. Not the number. Biggie, we're going back there now. I am only allowed to buy one chocolate. It's 1 for 1 customer. 1 photon will only take out 1 electron. So it means if we are 10, what have we done? We have increased intensity. Increased the number of photons. What's going to happen? We are going to get more what? Electrons. But we are all going to have the same change. Because we are all of the same color. I don't know if it's everyday shopping. When do I window shop? When I don't have money. Or I have money that is not enough. That's what I meant when I say suitable what? Frequency at the beginning. Not every, look, people go to the mall. Not everyone shops. It's not like everybody's broke. But what we want, we don't have money for. I see a shoe. That shoe is 2.5. I only have 2,000. Can I buy? No. I'm going to window shop. I am a photon with less what? And do you notice my energy is smaller than the work function? It means I have negative kinetic energy. I'm going home sad. I wish there was looting so we can go loot the shoe. You know, those kind of things. Right. But I hope it's making sense. It's everyday kind of business that we do. So do you see it here? Do you want us to answer this question? So, the examiner will tell you, why are these lines constant? Because they all represent the same what? Gradient, which is Planck's what? Constant. Which one of the following best explains the lines X, Y, and Z on the graph? Oh, the same metal. Okay, let's go back. We didn't read. The graph, I'm doing like Tesmia now. The graph below shows 3 different results, X, Y, and Z, of an experiment. Okay, nonsense. I thought they were saying something. A, the same metal with different threshold frequency. It's wrong. The same metal cannot have different threshold. It's like you go and you are buying the same chocolate from the same store. This one is 15 rand. This one is 12. The same chocolate, same brand, 15 rand, 10 rand, 20 rand. Something is wrong. Maybe one is expiring. Okay, so you cannot have the same metal. And if you remember, I did mention different metals have different work functions because of different ionization what? Energy. All right. The same metal with the same... Oh, wait. The first one. The same metal with different threshold frequency. Okay? The same metal with the same threshold frequency. Different metals with the same threshold frequency. Different metals with all different what? Threshold frequency. Because remember, smart, you've seen it already. What are these? FOX, FOY, FOZ. Do you see threshold frequency? The threshold frequencies are what? Different. Already, these two are wrong. Why? Threshold frequencies are different. And you cannot have the same metal. Check. D. Do you see how we answered that? Easy. Oh, beautiful. What do we have on the X? Frequency. Use a formula that has that X variable. So what is my E? E equals to what? HF. So what's my gradient here? H. Planck's constant. Make sense? Oh, what is X? Work function. First question. Let's leave. First question, Mark. Get it. Give a reason why photoelectrons are released when light. I'm going to give you the conditions now. But check. Which quantity can be determined from the gradient of the graph? Planck's constant. Calculate the magnitude of X. It's my work function. I can actually use gradient. I don't know if you get the whole idea. We can use what? Gradient to calculate that based on the information we have. But do you see? No, remember we didn't read. We are just checking quickly. I'm sure we'll be able to calculate. We'll be able to calculate somewhere. All right? Oh, by the way, remember, wait, hold on. I know that what? Let's see. Without even doing so much. Gradient is what? Delta Y over what? Delta X. Which is basically Y2 minus Y1 over X2 minus X1. Just to show you that we can get this quickly. Let's change this into this content. What is my M? H. What's on the Y? Kinetic energy 1 and kinetic energy 2. EK2 minus what? EK1 over, what do we have on the X? F2 minus F1. Let's check. Do I know my... Yes, we get it from the formula page. Now, I'm looking for X, guys, right? Do you know I know this point? Done. I know that point, so I can use this too. 50, okay, 0 minus x equals to 50 minus 0. Or you can, so if we were to write the coordinate, no, we cannot use 1, 110. Why? Because I don't have that energy there. But check here, what do we know here? X is what? 50, y is 0. What about my x? X is what? 0, and y is x. You see, we can get x2, x1, y2, y1, and everything there is equal to what? H. Check. Physics and maths got married here. Guys, do you see? If I were, okay, we wouldn't get here today, but I want to just show you something. This is circuits. I was trying to look for a graph question, but we'll see. L, I don't know what this topic is. It's L. Electrostatics. But check a graph. What do you have on the Y? F. What do you have on the X? Q squared. There's only one formula here that has F and Q. Is it? F equals to what? K, Q1, Q2 over R squared, right? Let's write it as Y equals to mx plus c. What's on the Y? F. What's on the X? Q. Oh, by the way, told us somewhere here, the graph below shows the relationship between force, and the product of two charges. The charges are identical. So it means that F equals to what? K Q squared over R squared. Let's extract our X. What's our X? Q squared. Oh, so this can be written as F. I'm bringing Q squared out. What do we have left? K over, do you see? We are done already. Mx plus C. Are you okay there? Somebody's saying, but there's no C. Check the graph. What is your C? 0. Y-intercept. So what's your gradient? K over R squared. I promise you they are going to tell us to calculate R. Do you know why? Gradient we can get from the graph by looking at any point here. Y2 minus Y1. What is K? It's a constant. What's the missing variable? R. Using they even specified. Using the graph, calculate the gradient. 7.1.4. Using the mathematical expression of Coulomb's law and the answer from the graph, calculate the distance R. Check for 7 marks. You don't know graph, you are done. No, from the graph. Y2 minus Y1. Any point. 4 minus 0 divided by 4 minus, my gradient is actually 1, makes life very easy. So 1 equals to what? K squared, no, K over, cross multiply. K equals to what? R squared. Do I know K? Formula page. The square root is the distance. I told you one simple skill that will affect you 8 times. Is it making sense? Okay, let's finish here. But you see that just by what we've done, you can actually handle any photoelectric effects, almost all photoelectric effect questions. Let's finish. It's been such a wonderful lesson. Guys, I definitely need to see you tomorrow. Whatever plans you have, fix it. Okay, conditions for photoelectric effect. Because you see, I'm not rushing this topic because I know it was probably rushed at schools levels. All right, conditions for photoelectric effect. And this will give you 5 marks. Conditions for photoelectric what? Effect. BB, okay, not the BB here. BB, are you still there? Number 1. W must be greater than threshold. No, sorry, E must be greater. Energy of the photon must be greater than the work function of the metal. Make sense? Otherwise, you are window shopping. Make sense? Shoaib, the day I don't have money, I visit you there in the shop. I'm just window shopping, you know. You can even chase me out. Security should take this person out. Number 2, I'm going to use number 1 to get number 2. It's just repetition, but in a different way. What is E? HF. Greater than what? HF naught. Can I divide both sides by H? It means my frequency should be greater. That's the second condition. The frequency of the light must be greater than the threshold frequency. And number 3 is to use wavelength. The wavelength of the light, check this one, must be less than. Do you know why I'm saying less than? Because F and wavelength are inversely what? Proportional. So the wavelength of the light must be less than the threshold what? Wavelength. All of this will prove to you that EK is greater than 0. Whenever, should you not understand and you get EK as negative, whenever EK is negative, there is no photoelectric effect. I hope that makes sense. Whenever is negative, there is no photoelectric effect. I have one last section to look at, and then we're done with the topic. Absorption spectrum and emission spectrum. All right, absorption and emission spectrum. Tabang, I hope it's worth your time. All right, that's the last part we're going to look at. Absorption. And from the word absorption, what does it mean? To take in. Emission means to what? To release. Okay, quickly. Let's look at absorption spectrum very fast. ESCOM is chasing me here now. All right. Absorption and emission spectrum. Absorption and emission spectrum. You can Google pictures of this just to understand. With colors, it's actually a lot nicer. I'll Google and show you as well. All right. Now, this is what we have. I'm just going to use a diagram to quickly show you this and then write underneath. Okay, let me do this. Watch this. I have a cold medium. Okay, guys, I'm going to do a lot of explanation here, so you just need to follow through. I have a cold medium. What does a cold medium mean? Electrons have low energy. I am then going to pass light through this. When I pass light through this, we pass what you call a monochromatic light. Okay? Mono simply means one, light of single frequency. Whether it's monochromatic or not, we pass monochromatic light through this. But the thing is, this must be a continuous spectrum. What we are going to see here will be an absorption spectrum. I'll give you a picture now to quickly help you. Absorption spectrum. Oh, now I got to run. All right, it's a colorful background with black lines. Black lines represent missing photons. And where are the missing photons? That have been absorbed. Oh, by the way, let's go back to electrons. Electrons absorb certain frequencies. Hence, they gain energy and move to an excited state. If you were to just Google right now, we'll check. I want to show you a picture of an absorption spectrum. I know you are writing. I'm sorry. Absorption spectrum. SPECTRUM. All right. Good. I wanted to quickly say that. Oh, no, I don't want words. Oh, yeah, there we go. What do you notice? Do you see the continuous spectrum? What happens? The light is a flow. There are no lines. Check your absorption spectrum. What do you see? Do you see a background? But you see missing photons there. Those photons have been what? Absorbed. Black is the absence of color. Is that okay? So for me now, I don't have color. Okay. Black is the absence of what? Color. So what happens? When we pass a continuous spectrum, light, through a cold medium, the electrons will absorb what? The electrons. Is that okay? So the electrons will absorb the photons. When I absorb a photon, what am I absorbing? The energy of the photon. What happens to my own energy? It increases. Let me show you something here quickly. Oh, I just love this. I want you to look at this. Check this. Check this. Now, do you see that electron there is moving around? You see, these things are called energy levels. Each of them are called energy levels. Let me see if I remember how this thing works. Okay, check this. Nap. Okay, interactive. Okay, jump. Okay, do you see what happened? There was a photon coming, went into the electron. Do you notice the speed of the electron has increased? Why? It absorbed the energy of that electron. Let's make it jump again. Do you see that? So immediately it absorbs the photon. What happens? Let me reset. There's something I want you to see. Check on the right side of your diagram. Those of you at home, on the right side, you would see where it says absorption spectrum. Do you see it's continuous? There are no black lines. Okay? Okay, reset, because it's doing emission already. All right? You see the first one? Let me allow it to jump. I want you to notice. Do you see there's a black line immediately? That photon was representing a color. Where is it? It has been absorbed. That's why you see a black line there. Let's go again. Do you see the next black line there? That one is infrared. So that is an absorption spectrum. The black lines simply tell you, oh, the photon that was responsible for that has been absorbed. What happens to the electrons? They gain what? Energy. And they move from a lower energy level to a higher energy level. Let me do the third one. Let's see if we can get the spectrum there. I'm not sure. Oh, it's beyond the chart. But I want you to check something. Check my emission spectrum. I am going to be releasing photons now. Let's go to 3. Oh, it's beyond the chart. But you see that electron that left? Let me do the second one. You see electron left. Oh, do you see that the infrared that was absorbed is now emitted? If I jump here, the ultraviolet that was absorbed has now been what? Released. Make sense? Absorption means we take the photon. So what color do we see? Black. Emission means we release the photon. Now we see a color. Okay. I've got 5 minutes. So this is how absorption spectrum happens. Make sense, everybody? Let's look at the opposite, emission. Then I'll look at the diagram that combines both of them together for you. Emission spectrum. They will tell you to describe how it is formed. Emission spectrum is formed when electrons from a higher energy level loses energy in form of a photon. They drop to a lower. They drop to a lower energy level. This is why hot medium becomes cold. Something hot, your coffee, becomes cold. Why? Energy is lost. Okay. Your coffee cannot be hot forever, no matter how sophisticated your cooler is. Okay. It won't be hot for, I use the word forever. If it can be hot for 3 days, I'll buy it. So these are energy levels. So let's call this E0, E1, E2, E3, E4. Guys, because of time, I'm going to just shut down the next 5 minutes or so. Load shed it. They're going to shed everyone now. However, guys, if you understand everything I've done, the calculations are not difficult at all. We just write whatever we have and then we substitute. But now I know I've covered all the topics. Other topics we've dealt with, we're just going to answer questions. And what we are going to do, guys, is I'm going to send you a paper, 2 papers. Okay? We just deal with papers now. And answer and answer and answer. All right, let's look at this. A, B, C, D, E. What do you think is happening on the A and B side? They're moving from a lower energy level to a higher. When does that happen? When they absorb. Okay, so this is what? Absorption. And when they emit, they release, they drop. It's called what? Emission. Here is the skill that I wanted to see. All these yellow lines, you see from here to here, it represents energy. Do you remember we said energy is directly proportional to frequency and energy is inversely proportional to what? Wavelength. It means, which one do you think has, look at all of this diagram, which one has the longest wavelength? Which photon has the longest wavelength? Or where is the longest wavelength represented? The longest wavelength. See, the longest wavelength means the lowest energy because they are inversely what? Proportional. A, yeah, multiple. This is the, this is what? The shortest what? Shortest wavelength, which means the what? E is very what? No, the E is the shortest here, right? Sorry. Lowest what? Energy. Therefore means the longest wavelength. Guys, I am done. I saw a question on this. Let's answer it together. So it's a multiple choice question. I am done. What is left for us is to, let's check. 2 multiple choice. The number of photons per unit time ejected from a metal surface depends on the, you answer it. Answer quickly. The number, don't forget, number. We're talking about number. The number. What's your answer? I'm waiting for those online as well. Please give me answer quickly. I want your answers. The number of the... You see, when you see the word photoelectrons, don't let it confuse you. We are still referring to what? Electrons. Okay? The number of photoelectrons, quickly. The number of... This thing simply means electrons. Don't worry about the photo. It's just a word. Number will only affect number. Which one talks about number here? Intensity. Done. So don't forget, number is only affected by what? Number. Lungelo, it cannot be. This one, do you notice that all of this frequency will affect energy? Wavelength will affect energy. Remember, E equals to what? HF. E equals to what? HC over lambda. Threshold frequency, it still refers to what? Energy. So this one is number. Let's answer this one. The diagram below represents 3 energy levels, X, Y, and Z, in a certain atom. The energy difference between level Y and Z is twice the energy difference between... Okay, that kind of things are very confusing. I just go for the diagram straight quickly. Okay, it makes sense now. They said between Y and Z, it's twice the energy of what? X and Y. Can I quickly ask you something? Is it emission or absorption? For them to move from high to low, what happens? They lose money. So they are emitting. It's emission. If the wavelength of the photon, in fact, to confirm it, check. If the wavelength of the photon released as a result of transmission P from level X to Y is wavelength. Oh, this is wavelength. What will be the wavelength of the photon released during the transmission from where? A transmission Q from X to Z. Anybody? 2 minutes, we sign out. B. A, B, C, D. B. What's your answer? B. Okay. BB? Or BB? Guys at home, quickly. What's your response? Guys, don't forget the relationship between energy and wavelength. What's the energy here? It's 3E. The bigger the energy, the smaller or the shorter the wavelength. It has to be a shorter wavelength because of the bigger what? Energy. So examiners want to play around with things like this for you. I hope it makes sense, right? Shortest wavelength. Thank you. All right. Guys, I'm very scared of this, guys. All right. So what we then do from here is, look, I'm done with the content. There's nothing else that you would hear from any place that I didn't mention tonight. The only thing is to do what? Is to calculate. Is that okay? And the calculation we will do. So now we're done with the topic, with all our topics. What are we doing? We're just answering questions. Okay. Let's communicate on the time. Just need to check on the load shedding schedule. But same time, most likely, tomorrow, we're good. Is that okay? Now, so please, what I'm going to do is, most of you are not writing. Is that okay?